Hello, my name is Muhammad Safwan bin Amir Karim. My matric number is 22148333. I'm from Group I. So our project is crime rate prediction using the hybrid model. So let's move on to the next one. Hello, my name is Muhammad Safwan and I will present you about background of the project. So the problem statement of the studies. The studies have shown a strong link between unemployment and crime. For instance, it's there been observed that 1% increase in unemployment can lead to 2% rise in crime rates. So in Malaysia, these issues become even more significant due to the rapid pace of the urbanization and increasing of the population density. So this put additional strain on law enforcement resources. So despite this challenge, there is still a gap in target research addressing how socio-economic factors like employment influence crime rate trends specifically in Malaysia. So this motivates us to explore the topic using a data-driven approach. So let's move on to objectives. So our project objective is to aim to develop a predictive model that uses historical data from 1960 to 2016, including unemployment rate and population data to forecast crime trends. So by doing that, we hope that provide uh, we hope to provide insight that will help policymakers and law enforcement agencies to design more effective strategies to combat the crime. So the next one. So why is this important? Accurate crime prediction allows authorities to allocate resources more efficiently, so respond proactively to potential crime surge and ultimately enhance public safety. So additionally, this project bridges the gap in understanding the socio-economic factors driving crimes in Malaysia, offering a unique perspective for policymakers. So in summary, this research not only addresses an important socio-economic issue, but also demonstrates how machine learning can be used to tackle complex real-world problems.
Bismillahirrahmanirrahim. My name is Ahmad Zulfahmi bin Zainal, matric number 2219235. So right now I will be presenting the data analysis part for our project. So for the data collection, we conducted the EDA on the population density file dataset. And then the dataset consists of 9 columns, which is year, states, density, total PC, which is total population count, total VC, total violent crime rates, total crime, unemployment, and then LAT long. So for the next part, which is data pre-processing. So the first one, handling missing data. For unemployment column, missing values were replaced with 0, since we presume that missing unemployment data indicates no unemployment. And then for the year column, we use forward fit method to replace the missing value, as the year column is in the dataset is incremental. And then for other columns such as density, total crime, and etc., we also use forward fill by grouping the data by the year column. And then for the second one, feature selection, we remove column like LAT and long, since we see that the column is unnecessary for our project. And then so we choose both column by dropping them. And then we check again missing values. And then for the next part, which is aggregation by year, why we aggregate the feature by year, because our data is represented for each state. So the data set is aggregated by year to calculate the total number of unemployment, density, and total crime. And then for the last part, we do data splitting, which is k-fold cross validation with 5 splits for robust training and testing. So for the next part, which is EDA, for EDA we have done some visualization to learn more about the distribution and connection between the dataset's important variables. So for the first one, we do population density for each state over year using line plot. So from this line plot, we can see that some of the insight that we can see is the first one, Kuala Lumpur stands out with the highest density and steady growth over time. And then states like Johor, Penang and Selangor also show consistent increases in population density, mostly driven by urbanization and industrial growth. So on the other hand, states like Sarawak, Sabah and Pahang, you can see they have minimal change, indicating less urbanization. And then we can also see states like Putrajaya and Labuan, at some certain points, we can see some spikes, maybe due to policy or administrative changes. And then lastly, states like Terengganu and Perlis maintain consistently low densities, probably due to limited urbanization and smaller population. To further understand the dataset's demographic, we also do line plot for population density over time, average per state, to examine the population density across the year. And then some of what are the insight that we gain from this plot. You can see that it highlights specific outliers or years with unusual fluctuation in density. So what are the cause or why it happens? We can see that it may be happen due to migration trends, economic shifts or policy changes impacting population distribution. So this analysis provides us with valuable insights into the pace of urbanization and demographic evolution in Malaysia. So next, we analyze unemployment trends and correlation between key variables in the dataset. So for the third plot, you can see we do unemployment over time. So this line plot tracks the change in unemployment rate over time, giving us a clear view of its fluctuation during economic recessions and recoveries. So we can see that patterns in unemployment are often influenced by broader economic conditions, such as shifts in population density or other social factors. So by observing these cycles, it helps us to identify periods of economic downturn and analyze their potential impacts on other variables like crime rates. Next, we also do correlation heat map, which provides us a comprehensive summary of the relationship between major numerical variables such as unemployment, population density, and total crime. So as you can see from the heat map, darker colors represent stronger correlation, while the direction of the correlation, which is positive or negative, helps us understand this relationship. So what are the findings that we can see from the heat map? First, we can see unemployment versus population density. It is densely populated areas often face higher unemployment due to increased competition for jobs in urban centers. And then for unemployment versus total crime, we can see a significant positive correlation, suggests that higher unemployment rates are linked to greater crime rates. So by exploring this relationship, we gain invaluable insights into the connection of social and economic factors, which help us to inform potential solutions to address this challenge. And last part of our EDA, we explored the relationship between crime rates and unemployment over time using a comparative line plot. So as you can see from the line plot, we can see how changes in unemployment often align with changes in crime rates, which allows us to investigate whether higher employment is usually associated with increased crime in specific years. So by observing this timeline, we can pinpoint periods of economic downturns or crises where both unemployment and crime rates spike. This pattern shows us that how societal challenges often amplify during such periods. So for example, during years of significant unemployment, people may face greater economic stress, which leads to the spike in crime rate as a potential consequences. So this trend highlights that complex relationship between economic condition and social issues, emphasizing the importance of addressing unemployment as a mean to mitigate crime. So that's all for EDA. We will be moving on to the next part, which is methodology. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Akimi and my matrix number is 2212529, and I will discuss about the methodology that we use in our group project. So we start with the flowchart. So we start by collecting our data from Kaggle, and then we need to do some data cleaning, which is all the details that have been explained by Brother Zulfahmi in the previous. So the data cleaning consists of some handle missing values. For example, we use a fill forward, and then we drop some columns if the value is 0, and so on. And then we make the exploratory data analysis, and we start the data pre-processing, which is we need to normalize and also splitting our data and do some feature selection. And then after that, we create or we start to do our model, which is the first thing first. We need to do our baseline model, which is we have three: linear regression, polynomial regression, and also the k-means nearest neighbor. So these are three model that we use to compare with our models. Okay, after that, we start to develop our model, which is we have exponential smoothing or ES, and also the BiLSTM or bidirectional long short-term memory. So these both models are developed separately, and then the result will be used will be used uh, for gradient boosting. So during the hybrid model process, the prediction or the result of the exponential smoothing and also the BiLSTM, it will act as input or features for the gradient boosting. So the hybrid model, we will predict based on the two predictions, and then we make another prediction. So we will analyze the result by using the mean square error, mean absolute error, and also R square. So basically, we will analyze every result. For example, for baseline modeling, we will have the result. For the exponential smoothing alone, we have the result analysis, and also for the BiLSTM and also for the hybrid. And then we will end our project. Okay. So this is the model overview. We use the BiLSTM and also the exponential smoothing. So the BiLSTM, which is stand for the long short-term memory or bidirectional long short-term memory, this is a type of recurrent neural network which is used for sequential data prediction. So this BiLSTM will help us to capture the pattern of the data in both forward and also backward directions of the time. So if we use the LSTM just predict or capture the patterns of the data only for forward. But by LSTM, it's stated that bidirectional, so it will capture for forward and also backward. Okay, the second model is the exponential smoothing. So ES is basically a traditional statistical method which is used for forecast time series data. So time series data is basically a data that consists of the time. For example, our data sets consist of the year. So the data will be based on the year. So that you mean by the time series data. So the ES model will focus on smoothing the data to make predictions based on the past observation. Okay. So what is the benefits of two of these two models? So the benefit of two models, the first one, BiLSTM, is a powerful model which is it can capture complex and also a non-linearities in some data set, and also relationship from based on the data, especially with some long-term and also temporary dependencies. For the ES model, it can effectively handle trends and also seasonality in the data. So it will see the pattern of the data and also the seasonality based on the dataset. Okay, next. Okay, for our hybrid model, this is just a model overview for a hybrid model. So we use gradient boosting. So why we use the gradient boosting? Because gradient boosting is a powerful ensemble model which combines prediction from multiple weak learners. For example, in our project is BiLSTM and also exponential smoothing to produce a strong predictive model. So gradient boosting will be used to refine the prediction by iteratively or by looping and improving the performance of the weak learners of the previous model. So this is some of the key features of the gradient boosting, which is the first one. It is a sequential learning. So each weak learners will correct the error of its predecessor by minimizing a specified loss function. Next one, it will emphasize learning from the previous mistake. So it will improve the overall accuracy and also prediction. And last one, flexibility. Gradient boosting can handle regression and also classification tasks. So based on our model, our dataset is a regression. So we will use gradient boosting to make the prediction based on our regression data. And also from our model or our methodology, our model is moving, or what can I say, the shape of our model is parallel, which is we run the ES and BiLSTM at the same time, and then we will combine the result by using the gradient boosting. So I think next I will talk about how we deploy the model. So that's all. Thank you. And just now I present about the methodology. Right now I will continue to the coding part. So this is our code for our model development. So this is all the inputs that we need to use during all the model deployment, including the metrics and also all the NumPy and Pandas matplotlib for our visualization. Okay, so the first one we need to load the dataset. So during the load dataset, this dataset is basically the dataset that have already been cleaned and also have been pre-processed. So the process of the pre-process has been done by Brother Zulfahmi in the previous. So right now we'll continue just for the model development and also deployment. So for this part, feature selection, I want to recheck or reconfirm that I choose the necessary features only for this model deployment. Next, I define the features and also the target, which is the target is total crime. It will predict the total crime based on the unemployment rate and also population density. But I just put all the features. Okay. Okay, so for the first step, we forget to scale the we forget to put this on the pre-processing data, but this is basically a normalization. So why use minimum or maximum scalar normalization? So it is the function, it is basically want to rescale the each features to a common range, which is to ensure that no single feature will dominate the other due to differences in scale. So basically, without scaling, features with larger values, for example, population density, can dominate a distance calculation or gradient updates in the algorithm, which is it will not help or not helpful for the prediction. Okay, and also the scaling will also ensure that the model will be sensitive to the magnitude, to the feature magnitude, which is it will treat all the features equally. Okay. Okay, we start to develop the model. So the first one, model development ES, or we can say exponential smoothing. So we will do the cross validation setup. We will do the cross validation setup with the time series split for the time series data, which is the time series data. So for the ES, we know that exponential smoothing is a time series model. So we need to we need to use the time series data to split the data into 5 sequential fold, which is each fold, which is this 5, which is each fold will include on the growing portion on the data for the training and also portion for the testing. Okay, then we will list out for all the hyperparameter for the ES model. For example, we have a trend, seasonal and seasonal period, which is all these three are the hyperparameter in the exponential smoothing. Why we list out? Because we want to do a grid search, which is we want to find the best hyperparameter tune for the exponential smoothing. Store the matrix or a combination of hyperparameter in this variable, and then we will start to do a grid search for for ES. Okay, so this is the grid search, which is we have a 3 hyperparameter, trend, season, and also the seasonal period. So we need to do the loops, and it will take some times because it is we provided 3 hyperparameter for each hyperparameter. So for the first one, for each fold, and then we will convert the year, so on, apply the ES on the training data set. It will fit into the model. We will train the model and also we will predict the model. So each combination of the hyperparameter will be tested one by one. So it might take some time, and also the metric evaluation will be printed for each model or each combination. So it will print the fold, the MSE, the MAE, also the R square. Okay, and then I will print the summary of the hyperparameter combination, which is I will average all the average metrics for trend, seasonal, and also the seasonal period. Okay, next I will use the data frame to print the summary, and then I will select the best combination or the best tune for the ES model based on the lowest MSE, which is the mean square error. Okay, next, so done for the hyperparameter tuning for ES model. For the second part, we use the BiLSTM model. We use the same thing, which is we need to refine the target and also the values, the target and features. But for the BiLSTM model, we need to reshape the data for BiLSTM input, which means we reshape the data. Why? Why we need to reshape the data? So basically, we reshape the data from a 2D input to 3D input. Why? Because a sequence model like BiLSTM, it expect input in the shape of 3D, which is samples, timestamp, and also the features. So reshape the data set will ensure the input conform to the format, which is we want to fit the data set into the model. So if we're not reshaping it, the model will treat the data as a 2D input, which could lead to errors and also unexpected result, and also will lead to bad accuracy of the result. So we need to reshape it first before we apply it to the model. Okay, and then we create the BiLSTM model by using the sequential, and then we add the bidirectional LSTM here, and this is the hyperparameter. This is the activation used, which is ReLU.
So my name is Alif Azmi Hakim Biazmin. I'll be talking about the result and discussion of our group project. So for the first part, we did the baseline model performance for our data set. So we did two parts of it, one for violent crime and one for the density over year. This is for us to get an overall overview of what the trend that might be in our data set. So for the baseline of the violent crime, we can see that key nearest neighbor regression has the least MCE compared to the other two, which shows that it will have the least mean square error compared to others. For the second baseline, we did is for density over year, which is to predict the growth of the density per year. So from this, we can see all three models meets the actual data or the prediction very closely, as the R square value, every each of it starts with decimal of 9, which shows that the data is fit with the model and can actually predict the actual density of the data set perfectly. So moving on to our advanced model performance. So for the first part, we did for the total crime. So to predict the total crime, for the first part, we use exponential smoothing or ES. For this part, we get R for the R square, we get 0.9148. This is a high R square, means that the prediction and the value is a good fit for each other. For the MAE, we get 9,818. This shows that for to compare between the prediction value and the actual data, it only has 9,818 losses unit compared to the prediction. And MCE, which is the mean square error, is 194,000 ish. This shows that it also has a high error. This is based on the MAE, so just a square of it. So for the next one is bidirectional long short-term memory or BiLSTM model. So for this model, we get an R square value of negative 0.2982. This shows that this model underperforms or doesn't fit the data that well. And the mean square error that we get from it is 49,000, which is very high compared to exponential smoothing. So therefore, it MCE also will be much larger compared to its before model, which is exponential smoothing, and it come out around 3 million. For the third model, we did is gradient boosting model. Gradient boosting model is the combination of ES and BiLSTM model together. It combines output from each of the model and produce it in one. So that's why for the R square, we get a value of 0.999, which is a very close, the best fit for it. And the MAE also decreases by 299, become only 299, which shows that the value that is off from the actual prediction is only 300. The MCE also decreases and it only become 166,000 ish. So the last graph is the combined model, which is the final one, which combines ES, BiLSTM, and gradient boosting at one graph. For this one, we get the perfect one score for the R square, which shows it is the best fit for our data and based on the prediction. You can see from the graph that there's no difference between the prediction graph and the actual data. It shows that the model is being able to predict the total crime perfectly. The MAE also is the least compared to others, which only 3.23, which is very small compared to other values from the other models. And also the MCE is square of it, so it will be least. It's only 27.17. So that's all for me. Thank you.
So in this study, we developed a hybrid model that combines exponential smoothing, BILSCM, and gradient boosting techniques. This model demonstrates exceptional predictive accuracy, achieving an R-square value of 1 and a very low mean absolute error of just 3.23. These results highlight the effectiveness of integrating statistical and machine learning methods to capture both short-term and long-term trends in crime data. Our findings confirm a strong correlation between unemployment rates and crime rates, with population density also playing a significant role. This insight underscores the importance of addressing socio-economic factors in crime prevention strategies. So while our results are promising, there is still room for improvement and expansion. So for the first one is incorporating additional variables. So factors like education level, economic policies, and urbanization rate could provide a more comprehensive view of the drivers behind the crime trends. The second one is exploring other domains. So the hybrid model we developed is versatile. It could be adapted for applications like traffic prediction, environmental monitoring, or even public health. And then the last one is testing advanced techniques. We plan to experiment with other ensemble models and fine-tune the BiLSTM and exponential smoothing components to further enhance the performance. So I think that's all from me. Thank you.